Moving on to the second part of the proof of the Zk-SNARK. So now we know that the issue is the challenge is about proving that you know a linear combination of these polynomials A1 to A6, B1 to B6, and C1 to C6, such as A times B minus C is equal to polynomial H multiplied by polynomial Z, where Z is this one, x1, x2, x minus 3, x minus 4. And we want to show that we have this A, B, C, H, while not sending the whole polynomial because it's too big, while hiding our linear combination, so the factors of the coefficients of our linear combination, in a way that the verifier can check that this is indeed a linear combination, and that this statement is valid. Okay, so that's the problem statement, and for this we need a tool which is going to be based on the elliptic curve cryptography. So let's get a little bit of like theory about how they work, just enough so that we can understand how the Zk-SNARK work. So first of all, everything that is done in crypto is done with integers. It's not done with real numbers. So we use numbers that are so far real numbers. So numbers are on the any number between 0, minus infinity, plus infinity, and in the continuous space. But in reality, what computer cannot do that. I cannot represent any number, arbitrary number, and the math is actually done only in integers in a particular range. So the range is actually quite large. So these are numbers between 0 and big N, or N minus 1 if you prefer. These numbers are really large, and it's typically like in the order of 2 power to 56. So in the order of 2 power to 56. So it's quite a large range in there. But it's not all the numbers, obviously. It means that all the math that we're going to do is modulo that particular n. So it's really z over nz. That's how we write a set that is a modulo particular number. So essentially, this is like a clock. If you have 60 seconds, it goes back to 0 second, and you roll out 1 minute. But if you don't ignore the minutes and the hours, then this is like if every 60 seconds, the set where you roll back, you wrap around. So here you will wrap around when you reach n minus 1 is the last number that is acceptable, and you go back to 0. In this set, most of the if you choose n appropriately, most of the operations will still work. You can add, you can subtract, you can multiply, and you can divide. But the other interesting thing about this set is that some of the operations are significantly harder to do. So in particular, division is harder to do. Furthermore, they use these numbers to plot a curve. So there's an elliptical curve which has a shape y2 called ax cubed plus bx plus c. So that's an elliptical curve. So it's symmetric in y. It's not an ellipse, it's elliptic curve, and is depending on the choice of A, B, and C, it has different shapes. So the one that they choose is it has this shape, something like that. And again, this is plot with x and y continuous here. It's a continuous curve. But in reality, we're only interested in numbers that are integer and in this particular range. So it's really like scattered, like more like scattered points. And on the set with these points, you can define an addition. So you can define the addition of 2 points. So if you have point A and point B, there's a way to define a point A plus B. Let's call it C, somewhere on the curve, such as the standard operations of standard rules of addition still hold. So in particular, that you have stuff like A plus B plus C is the same as A plus B plus C, and other things like that. So having a particular addition rule of operation have these properties make it very useful, because a lot of these theorems do not care about actually the form of the operation, but just that the operation fulfills a particular set of conditions. So I'm not going to enter the details of exactly how this addition is implemented or anything, because we will go too far into the details. So there's definition, and the interesting thing with this addition is that based on it, you can define a multiplication by a value. So you can add points, but you cannot multiply points. It's only addition of points, right? So we should do A plus B is okay. Okay, but A times B is undefined. What you can do is to say that if you have a point, you can add it to itself, and then you can repeatedly do that. So by doing that, we define this to be 4A, 4 times A. And because you have these properties, this notation is also kind of works the expected way, in a sense that if you have N and P, which are numbers, not points anymore, and you define NA and PA, then you can do NA. This is a point, right? This is a point B, and you can do PB as well. So PB is by multiplying this point by P, and it happens that this is also going to be equal to NP.A. And that's kind of obvious, because what you do here is that in A you add 8A n times, and then you repeat this operation, because this is B. So you do this n times, and you repeat this time P times. So it's the same as doing A n P times. All right, so these are some examples of stuff that you can do with once you have this operation, this addition. And the way they constructed this addition and the choice of the curve and the parameters A, B, C, and N here is such that if you have chosen N sufficiently large, so it's inside this set, not exactly this set, but in this particular, it's around that range. You have and you have chosen it very sufficiently large. It's easy, relatively easy to do the multiplication. So you can take any point and then calculate this. But once you have, so let's call this point B. Once you have B, even knowing that B is A added many times, so you know A, you know B, it's extremely hard to find N. And extremely hard here means like it's the theory that it exists, but we don't have the algorithms, the computation, the computer's strength, or the algorithms or the techniques that are required to inverse this operation, to revert, to calculate the inverse of this operation. So it has to be hard. If you know it's not hard, then most of this stuff will fall apart. And to make it hard, the choice of these values n, a, b, is quite important. So knowing that you have this, you can also then fix one point, because this point here, a, is not really significant, because it has to be hard anywhere. So we can also give one reference point. Well, it's called g. So we choose one point on the curve to start with, a pretty common point, I would say, and say that from now on, every time we do we go from n to a point. So n is this number, right? And we go to a point. We actually mean that we need to multiply g by n. So the point g is a reference point that is part of the parameters of this curve, right? So we choose the curve and we choose the point on the curve, right? And all this stuff is known. So for Bitcoin, for example, the curve has a name. It's called, it has a name, and it means that all this stuff is known once you have chosen the curve. Okay, so that's how we go from numbers. These are numbers between 0 and -1 again into points. And the idea here is that when you talk about secret and public key pairs, so we are talking about this pair. So this is a secret. So, and this is the public information. You would generate this pair easily because you first choose n randomly. That's your secret. And from the secret, you can derive this public information just by multiplying with g. But if you give, if somebody only knows ng, he will not be able to reverse this operation and find n. So that's your secret and public key pair. So if you lose, of course, it means if you lose n and you only know this part, then you're like everybody else, so you will not be able to find n. Another thing that is interesting with already we can do with these what we have done so far is to hide our knowledge of n of these secrets by the fact that we have this property ng here. So let's say that you have n p and let's call it let's call it npq, and you have you know that there's a relation between these guys, this relation. So not every relation will work, but if it's a relation that is linear, so it could be n plus p plus q, or it could be 2n plus 3p equal q. Anything that is a linear combination here, it will work, in the sense that if you have this and now you go from secret to public, so you have you generate the point that matches n, p, and q, and we call it big N, big P, and big Q, right? Again, it's just by multiplying by g. You will do like for n equal n g and so on and so forth. Then this relation would also would also be valid with the points. You would also have that, and that's fairly easy to see, because basically what you did is if you have this equality and you multiply everything at each side by g, right? So you multiply each side by g here. QG will become this big Q, and this guy here, this product here, because you have these properties, you have these properties, you can pull the G inside, so it becomes 2ng plus 3pg, and then that becomes 2ng, and that becomes 3pg, and that becomes 2n plus 3p. So this is equal to q. by this the properties that we have about the point addition. So that's why it's super useful that we have this thing works out. And so this operation is very interesting because it means that if you have a linear relationship between the secret, so a linear relationship between values, you can transform that into points and still have the same relationship verifiable. So a guy who receives a P and Q can verify that this relationship stands. Yeah, he can do that, and you can multiply n by 2, multiply 3 P by 3, and then do the sum and check that it's indeed equal. He finds the point Q, and if you were able to produce this, it means that you were able to have this guy, right? Because there's no way for you to go back. Right? So it does mean also that you know the source points were also valid. Okay, so that's one thing that you can do with the fact that the way we define they define this transformation from secret to public point. But that's in itself is not enough for what we are going to need later, and we need to do also. Because this is only limited to linear combinations. If you have something that is a relation that is it's like n times p equals q, right? So you have this equality. This would not translate to anything that you can write about np and q. In particular, if you say that it's n times p equal q. That doesn't even make sense because n times p is not defined. Right? There's no meaning to the product of 2 points. So this is clearly wrong. And we can't do, with the current tools that we have, we can't express this relation between secret values into a relation with over points. So we need something different. And they have found something called pairings, which is very complicated. But what we're going to do just is use them. So we're not to prove. I can't prove anything about this. It's too hard. But we can see how we can use them and what they can do. So so then here, so far we had like an operation that goes from n to n. So it goes from numbers. So this goes z over nz, right? So some set here of numbers, and it goes to the space of points. Right? So the point, we'll call it like I don't know, set of points. So points. Right, and what we're going to use now is so it's only one parameter basically. It's a function that takes one parameter and then creates a point. So now it's going to be a function that takes 2 parameters, and this time the parameters will be points. So I'm going to start writing points as capital letters, and these guys are lowercase. So if you have A and B, this is an operation that is defined on points. And furthermore, if we say that these are produced by going from a secret. So if we say that A is little ag and little bg, right? Actually, it works on. It doesn't have to be like this. But if you know that A is ag and B equal to bg, then you have this equality A power B. Right. In a more general definition, it's bilinear. So this is a bilinear form because if you have if you have P, Q, right, and then you add R on one side, so it's equal to PQ times RQ. Right, so the sum here became product basically. So you could expand the plus into some product if it's on the left side, and the same is true on the right side. So if you have P, Q plus R, it's also equal to PQ times PR. So this is actually the more general definition. But if you have this, then obviously you have that as well, right? Because what you do here is that A is if it's A is AG, then you have G plus BG plus BG A times, right? G plus BG is a division of AG, right? So you have a sum of G A times, and then if you use this equality A times, then you will end up multiplying GG A times, so it's the same as A GG power A, and then you do the same on the other side, and then it's the whole thing power B, so then B becomes that's of power A times B. But we are going to use this form here rather than this form here. So what this guy give us? Okay, so just this one. This is the good stuff. Is now the ability to express a product of secrets as a relationship on points. So we have this guy, and if we have now the matching points, so it goes to N, it goes to P, and it goes to Q, then we can say that if we do calculate E of NP, right? So it's equal to E of P to NG. And E of P of G, that's equal to E of G NP, right? So this is the same relationship as this one. And if we do E of Q and G, then it's equal to QG G, and this is equal to E of GG power Q, right? So now we can see that that if these two guys are equal, this NP and EQG are equal, that means that these two guys are equal here. So these two guys are equal here, and that means that NP is equal Q, because we know that EGG is not 0, right? So this equality here means that the exponents are equal. Okay, and also, as long as it's not too big and we wrap around, but anyways, it's fine. So we have this equality of all costs. It's also there's a modulo somewhere, right? So everything is inside this set. So it's always going to be equal modulo a certain number. So, but this is what you want to have. So then you can express linear combinations with the other rule. So put together, we have the ability to express linear combinations like that, as well as the product. So it doesn't go beyond that, but that's not actually enough for what we need. Right? So yeah, this is the only thing that we're going to use in the next section. So now, why do we have that? Okay, going back to the stuff that we wanted to prove. We wanted to prove this guy, and the point here is that we can't send the whole polynomial. So what we're going to do is we're going to use a property that they're going to use a property that if you have two polynomials that are different, so if you don't have exactly this solution, but you have a slightly different polynomial, they will be different at most points. So, and that comes from the fact that regardless of how many degrees you have, the polynomials have a fixed number of degrees of liberty. So I mean, in other terms, it's because for example, if you have a polynomial of degree 2, you will have a parabole, and then you can match another parabole. So these two guys are equal, but only at these 2 points. So they will intersect at 2 points, but anywhere else they will be different. And if you want to have more common points, so you're gonna naturally pretend that they're equal. So somebody would come and say, okay, are they equal? And then they would check from some point, and you say, okay, they equal here and here. But as soon as you check another point, then they will be different. And you can try to match more and more. So you can use a third degree polynomial, fourth degree, but it will just add a few more points. And if the verifier comes and really chooses a random point, here he has access to 2 power 256 roughly different options, which is like 10 power 70 or something like that. So I think it's 10 power 70. There are way too many choices that he can take. So there's no way for you to pretend that these two polynomial match if the checker can have pick on where he's going to check. So the bottom line is that you don't have to show that you have exact polynomial, but you just need to show that at a random point your polynomial matches the right solution, and it's already believable because the chances that this is going to match for another polynomial is extremely low. It's about 10 power minus 70. Which means that this obviously only works if the choice of the point where you check is unknown. Because obviously, if you know in advance that you're going to be checked on that particular point t, then you can make another polynomial that matches that guy here, and again nowhere else. But you know in advance the question of your exam. And then you can pretend that you are very good by just learning the answer to that particular question. So the choice of t here has to be random, and it has to be random for so it's not like random in the sense that we're not going to choose a different t every time, because you will see that it's not only t that we need to calculate, but we also need to give a certain number of values derived from t. So we can't just like every time we do a verification, we give a different t. But what we can say is that provided that nobody knows really the t, it's the verification and the proof will be good enough. The proof will be good enough. So what we say is that instead of having this equation true for a polynomial, we're just going to be saying that it's true. So it's a, right, at the given point t. Right? H times h of t times of t. Right. So only at a point, not everywhere. And furthermore, so these are points. We want to hide these values. So instead of giving you or the prover gives you the real values here, he wants to hide these values because he knows that this is derived from that guy. Right. So how does he calculate this? First, he's giving basically a1 of t, a2 of t, and so on to a6 of t. Right. And knowing these base values, basically, he can do the linear combination. right? He does a linear combination here. Then he will achieve, or you calculate this guy, right? Just by doing this same, but with the values that were pre-computed. And again, since he wants to hide the linear combination coefficient, he's not going to give a of t. He's going to give the point that is matching that particular secret. So he's going to multiply by g. So how does he calculate this? Well, he's not actually getting this one, a1t, a2t. He's also getting these as points. So he's getting all these guys. And the same for the other guys, for the B's and for the C's. So B1 to B6. And then the C's as well, C1 to C6. Calculated at T multiplied by G. So it's calculated at point T and then hidden. So this you can see why the choice of T should is important to be forgotten, to be destroyed. So based on this, right, you can calculate A, B, and at T times G, and then C at T times G. For H is a bit harder because H is it's not a linear combination of these guys. Right? H is the residue after you divide by Z. So H is has a lot of different options. It can be pretty much anything, but H is, we know that H is a polynomial. And again, we want to calculate H at T G, right, like the other guys. But we know that H is a polynomial. So if you have TG, so you have G, TG, T2G, T3G, and then lots of them, then you can use these reference points to calculate a linear combination of them, and then you would have H of T of G, because H is actually also a linear combination of these guys by the fact that it's a polynomial evaluated at T. Right? So this gives the prover a way to derive points. So these are going to be points instead of the values of the polynomial at this point. So how can we say that they are points, because we already use the capital. Okay, let's just say that in the future A, B, and C are now points, right? So we have now A will stand for A T times G, and same for B and C. So now we have something about A, B, C, H, right? So we can use the pairing that we have defined before to find what relationship these guys should have in order to check that the values that they were derived from, A, B, C, H, is this one, right? So you can see that this relationship has a multiplication here and another multiplication here, right? And otherwise is linear. So we can use the same trick that we just saw, where we use a pairing of, now is A and B. Right, so this is this will capture this product basically, and then we have C here. So before we had remember the example was NP equal Q, right? So basically we were doing NP minus Q equal 0. Right, now we have NP minus Q equal R times S, right? We have something like that. So that's the same technique is E of AB divided by E of CG is equal to E of H HZ. Right. So that's the same. You can develop this guy. This guy would become, so this term would become, you can see here, this term would become GG of A times B. This time will become E of GG, but we only use C up there. And then this one is become E of GG, and then H times Z, right? So now all exponents means that this is going to be A times B minus C is equal H times Z. Right. This is, we come back to simulation, and this is going to be the check that the verifier would do. So he can do this verification on the points that the prover gives to him. So this establishes that once the prover gives him these points, the verifier can check that these points matches the polynomial relationship. So now they are hidden because they were multiplied by G. So the verifier cannot figure out what was the original value, but the prover had to know them, otherwise he would not be able to generate these points. Right. And so this answers the part where it is succinct, because now we're not sending the whole polynomial, we're just sending, so far we're sending 4 points, right? We're sending A, B, C, H. So it's just 4 points, so it's pretty small. It's zero knowledge because these are points, these are not the values. This is verifiable. So we have all this stuff, right? But there's obviously one issue, and the issue is that the prover can completely cheat, in the sense that when he sends the points, A, B, C, so A, B, C, H, now they are blinded. So they were sequence multiplied by G. So there is the verifier cannot be sure that actually these values were obtained by doing a linear combination of A1, A6, B1, B6, and C1, C6. The prover could have pretended to give linear combinations, but he just found out pickup points, and because it's really easy to make points that matches this relationship. Sorry, this relationship here. If you don't have to also have these guys, right? So the second part of this is to force the prover to have A, right, being a sum, some linear coefficient of the points that we are given. So we were given basically these points, right? So these terms here were the stuff that's given to us, and he has to do this guy. So the trick here is also derived from the fact that when you have a secret and you have a point, you cannot go the other way. So if you have G and you have N, you can calculate NG, but you cannot calculate N anymore. Right. So what the challenge would be is to produce pairs. So this is a pair basically, right? We have G and NG. They are paired because there's a coefficient N that scales between them. So going from G to NG, you take the first value, first point, and you multiply by g to get the second point. So if given a value lambda, we say that we have a valid pair if you have a point A and a point B, such as B equals lambda A. Right? Basically, B is A scale up by multiplying by lambda, by adding lambda times. So this is a good pair. And now, if you are somebody who doesn't know lambda, so it's very important not to know lambda. So lambda is unknown. If you have C and you create a pair as well, so you giving C, so you can choose C as you want, but you are challenged to give D, such as D is also equal to lambda C. So you must give a valid pair as well, relative to this lambda. So this lambda is arbitrary. It's just not known to you what the value is. So the challenge here is that if you must find the D that matches the C, you cannot do that without knowing lambda. Because if you know lambda is trivial, but if you don't know lambda, you cannot reverse this equation. You cannot go from B A to lambda. Therefore, you also cannot do this. You cannot derive this. This is an assumption for this to work. I mean, I don't think that there's a real proof of this, but it seems to be quite okay to assume. So the only way for you to provide another pair, so you can choose C whatever you want, right? You just shouldn't be A, otherwise it's trivial. So the only way for you to provide such a good pair, and C is not 0 because it's trivial, is to take the existing pair that you are given, and also multiply by something. So obviously, if you choose any alpha, you can do alpha A and alpha B, right? And this will also be a good pair, alpha A and alpha B, because this lambda will be inside. This is going to be alpha lambda A, and obviously this lambda alpha A. So now you have a good pair. This is a valid pair, and the idea here is that you can only give a valid pair if you are taking something from something that was given to you and scale up, multiply by something. If you are given more than one pair, so now we have A, B, and C, D, and this holds true, you can also do linear combinations. Right? So you can also do A plus C and B plus D. That will also work because this is lambda A plus lambda C, and it's called lambda A plus C. Right? So A plus C and lambda A plus C. So this is also a valid pair. So any linear combinations of whatever you're given will work out, will be a valid lambda pair. So using this, we can extend, we can verify that the prover is indeed using linear combinations, because during the setup phase, they created a T of G. So we know that these values were pre-computed and given to the prover, but we also generate the matching value in the pair. Again, this lambda is unknown and has to be destroyed. So now, if instead of saying that we have only these points, we also have the partner, what was it, the second term of the pair. Sorry, 6 here, and same for B and same from C, right? So all these are now pairs, and you give this. Then if the prover made a linear combination of these points here, and it does the same with this point here, he will obtain A and something which is also a lambda A, right? So A of G, A T of G, and lambda A T of G, and that would be a valid pair. So the only thing that's left for us to figure out is how the verifier can check that this is indeed a lambda pair if he doesn't know lambda. So he doesn't know lambda, and that's because the verifier is also could also be a prover in a different scenario. So if he knows lambda, then basically everybody would know lambda. So he must not know lambda, but yet he must be able to verify that the prover has given him a valid pair, and that's also can be done through the pairing. If you have, so because this is a relationship, if you have something that is a pair, so if you have something that is written as lambda a, right? We know that it means that there's some little ag, little lambda ag, and we know that this is basically e of gg a square lambda. But more importantly, if you have another pair, b and lambda b, now you can calculate the kind of like the cross of the two. So you can have e a lambda b, right, and then e lambda a b, right? So you have two pairs, right? You have a good pair. Okay, so that kind of forget about this one. It's not very useful. You have already a good pair because these are you got actually tons of pairs from the setup. So you can pick one of these pairs, and now you are receiving something that claims to be b lambda b. Right? So you calculate this. So this is not lambda b. This is okay. This is something that just claims to be lambda b. But if you calculate this, you figure out that this is going to be ab power lambda, and this also should be equal to e ab power lambda. So you would have equality of these two guys, these two pairings, if and only if this was indeed lambda b. If it was lambda prime b, so not the same lambda, then you would have here lambda prime, and it would not be equal. Lambda would not be equal to lambda, right? So only works if the two guys are equal. So all this put together, you have the whole picture now. You, as a prover, we recap the whole thing. As a prover, you go through the motion first of converting the problem statement. Where is it? Yeah, you first convert the problem statement to an arithmetic circuit, which involves variables and gates. That gives you a circuit like this, that then you turn into a set of equations for a constraint system of rank 1. So that would be a set of ABC, where ABC are vectors. The dimension of the vector is a number of variables, because the solution would be the assignment of these wires. So variables and wires are the same thing here. And you have as many sets of ABC as you have gates. You have these boxes. Then step 2, sorry, step 3 actually. Step 3 is to convert from this rank 1 CS into a QAP, into a quadratic program. Also, essentially turning the equality, these four sets of equalities into one equality, one constraint on a polynomial that must be true at 4 different points. So that's the phase where we produce this guy. So this is the third step. Then we say that we want to prove that we have such a polynomial by generating the points. Like when you reach this, you already have these guys, and you also have this guy H. Right? Then you use that to produce the matching points, and that's what you send. So for the prover, this is all it has to do. The verifier then takes these points, verify through pairing checks that these points and their lambda scale up are okay. So the prover sends A and lambda A, basically B and lambda B and C and lambda C, right? Then the verifier verifies that this is indeed valid pairs through the pairing check. Then he verifies that this relationship holds true for another pairing check. And the last thing he has to do, actually, that I forgot to mention, is that these linear combination, they must be the same, right? So what we have verified through this technique here was that the A is a linear combination of A1, A6. B is a linear combination of B1, B6. Same for C, but it didn't imply that the same coefficients were used in these three linear combinations. So there's one fourth point that you have to give, which is basically a combination of A1, B1, C1, such as if you have, for example, if you have A1 plus B1 plus C1, well, in a way that doesn't mix the coefficient. So if you just do this, they are polynomials and of the same degree, so the coefficients will like mix together. But if you do A1, B1, but you multiply this one by t power 6 and then this one by t power 12, you have a bigger polynomial where A, B, and C do not mix. So once you have this guy and you have the same thing with A2, B2, C2, you can use the same trick as with the lambda guy to make sure that if the guy indeed did linear combination with different coefficient, then this relationship will not hold true anymore. Right? So that's a bit like hand waving here, but that's the idea of this particular additional check, and just so that the prover cannot use different linear combinations. Okay, so if you have A, B, C with their lambda pair plus this guy and then H as well, so that's like 4 or 5 pairs. Then the verifier can check that everything was calculated properly.